Have you ever wondered if it's possible to build the perfect piece of software? I mean, a program that could look at any other program and tell you with 100% certainty if it's going to crash or just get stuck forever. Well, it turns out that's not just a hard thing to engineer, it's actually logically impossible. So today, we're going to crack the code on the halting problem, one of the most famous and famously unsolvable problems in all of computer science. Let's find out why perfect software is, well, just a dream.
We have all been there, right? You're in the middle of something important, and bam, the program freezes. You get that spinning wheel of doom, and you're stuck. A lot of the time, the reason for that is the program getting caught in some kind of loop it just can't escape. So you can imagine the ultimate dream for any programmer. Could we write a master program, an ultimate bug checker that could scan any piece of code and warn us about these infinite loops before they ever happen?
Now, sometimes a program is supposed to run forever. Think about your phone's operating system or the software running a website. You don't want those to stop. But other times, it's a bug, plain and simple. This little snippet of code you see here, while true, continue, is like the classic example of an infinite loop. It literally tells the computer to just do nothing forever. So the real problem is figuring out how to tell the difference between the good intentional loops and the bad crash your app ones.
All right, so this whole challenge of telling the good loops from the bad ones, it leads us to a really big idea. What if we really could create that ultimate bug checker? A single, genius program that could look at any other program and solve this problem for good. I mean, it would be the most valuable piece of software in the world, right?
This is what computer scientists officially call the halting problem. Let's break it down. You take any program and any possible input you could give it. And the question is, can you figure out if it will eventually halt, finish what it's doing and stop, or will it just run forever and ever? So, to really get our heads around this, let's pretend we've built it. Let's give our amazing hypothetical solution a name. We'll call it Halts Checker. The idea is simple. You feed it any program's code, and it spits out a perfect, simple answer, either halts or loops forever. Sounds simple, sounds powerful, and, as we're about to see, it's completely impossible. So how do we prove something like Halts Checker can't exist? Well, we're going to use a really cool technique from logic called proof by contradiction. We're going to design a brand new, very, very sneaky program. Let's call it our troublemaker, and its only job in life is to break our perfect bug checker.
Okay, the logic behind our troublemaker is just brilliantly simple. First, it gets its own source code as its input. A little weird, but stick with me. Then, it uses our so-called perfect halt checker to analyze itself. It basically asks the checker, hey, what do you think? Am I going to halt? And here's the kicker, the absolute crucial part. Whatever answer halts checker gives, our troublemaker is programmed to do the exact opposite.
So here's what that contrary logic kind of looks like in code. Our program, let's call it G, uses the halts function, that's our halts checker, to ask about itself. Now, if the halts function predicts, yep, G is going to halt, then the program's instructions immediately force it into an infinite loop instead. But if halts predicts, nope, G is going to loop forever, then the program is designed to just stop. It is a perfect, inescapable paradox.
So we have our supposedly perfect halts checker on one side, and our paradoxical troublemaker program on the other. The stage is set for a showdown. Let's see what happens when we feed the troublemaker into the checker.
This is the moment of truth. Right here. We take the troublemaker's code and we feed it into halts checker. Now, halts checker has to give an answer. That's what it's for. It can only say one of two things, halts or loops. So, what's it going to be?
And this is where the whole idea just completely falls apart. Let's walk through it. So, let's say halts checker looks at the code and says this program will halt. But wait, what are the troublemaker's rules? If the checker says it halts, it's programmed to loop forever. So the checker was wrong. Okay, fine. Let's try the other way. Halts checker says, okay, this program will loop forever. But again, the troublemaker's code says that if it hears that, it should immediately stop or halt. So the checker is wrong again. No matter what it says, it's wrong. It's trapped.
See, the checker is completely stuck. It is logically impossible for it to give a correct answer. And that means the only possible conclusion is that our very first assumption, the idea that we could write a perfect all-knowing halts checker in the first place, that assumption has to be false. A program like that simply cannot exist.
Now, this isn't just some clever brain teaser. This conclusion points to something really deep, a fundamental limit to what computation can even do. It's a boundary that no amount of fancy programming or supercomputer processing power can ever cross.
And the person who first figured all this out was the absolute legend Alan Turing. And he did it way back in 1936. Think about that, before we even had what we would recognize as modern computers. His proof showed, for the very first time, that there are problems out there that we can clearly describe, we can define them mathematically, but no computer ever can be programmed to solve.
Turing's work didn't just come out of nowhere. It was actually a direct answer to a huge question posed by the great mathematician David Hilbert in 1928. Hilbert asked, essentially, is all of math solvable? Can we find a surefire method to solve any mathematical problem? And Turing's proof basically showed that, at least for computation, the answer is a big, resounding no. And here's a fun fact for you. The name halting problem wasn't even used until 1952.
Okay, so a theoretical puzzle from the 1930s proves a perfect bug checker is impossible. That's cool, but so what? Why is this so important today? What are the actual real-world consequences?
Well, the implications are actually huge. This isn't just abstract theory, it affects almost everything. It sets the absolute upper limit for things like automated software testing. And here's a big one. It's why a truly perfect antivirus program is impossible. Think about it. For an antivirus to be perfect, it would have to predict the future behavior of any new program to see if it's a virus. That's just the halting problem in a different costume. This limit is so fundamental that it's been generalized by something called Rice's theorem, which basically says you can't figure out any interesting, non-trivial thing about a program's behavior just by looking at its code.
So here we are. We've built these incredible machines that can calculate things at speeds we can't even comprehend. And yet, we've also proven that there are simple truths that are forever beyond their reach. It shows a hard, undeniable limit to what algorithms can ever know. And that leaves us with a final, really fascinating thought. If our most logical, powerful creations have these fundamental limits of knowledge, what does that say about our own?